So hello everyone, welcome to a Small Terrible channel. This is Mr. Aseno, your teacher for today. Today we're going to discuss about force, motion, and energy. This is Science 8. For our first session, our topic is force, acceleration, and constructing a free body diagram. Are you ready? Are you excited for our lesson for today? All right then, let's start. So this is our first quarter, week one. Our learning competency would be investigate the relationship between the amount of force applied and the mass of the object to the amount of change in the object's motion. That is our learning competency focus. Because actually, this learning competency is based on the second law of motion. But for us to be able to really understand this second law of motion, which is our focus of the learning competency, we need to have a good foundation in the first law. So we will have two sessions for this competency rather. So we have session 1 and 2. Our objectives for the sessions: first, we have to recall important concepts of motion from grade 7 science. Then second, we are going to construct and interpret free body diagrams for various situations. And third, differentiate between balanced and unbalanced forces. Fourth, explain Newton's first law of motion. And then lastly, we're going to cite examples of situation demonstrating Newton's first law of motion. Okay, all right. Now, let's look at the picture. Before you start guessing which among the cards below is the heaviest, you try first to name at least 5 physics concepts that you can relate when you see a loaded shopping cart. I'm pretty sure you're so fond of shopping, right? So, okay. So we'll be given a few minutes to give at least 5 physics concepts based on the picture presented. I know you are a great learner, so you can easily formulate. Okay, you learn a lot from your grade 7. Okay, and you're done. Okay. Now, for 5 minutes, we're going to use your meta cards. Then differentiate the terms speed, velocity, and acceleration. These three terms actually are very important because in physics, we usually and most of the time encounter this concept. And we have to have a good foundation in understanding this concept, or else we will not be able to understand the laws of motion. Okay, then. So next, you are going to post your meta cards on your designated area. Okay, you are given 5 minutes to do this. So differentiate terms speed, velocity, and acceleration. Right then, good job, you're done. Now, let's talk about speed. So speed is simply how fast, meaning it answers the questions how fast. For example, 100 meter per second. Speed also is a scalar quantity. What do you mean by scalar quantity? Scalar quantity means it only gives the magnitude but no direction. So in that example, speed, we have 100 meter per second. It talks about magnitude, but no given direction. So speed is an example of a scalar quantity. It answered the question how fast, and a good example is 100 meter per second. Only the magnitude is given. Okay? Okay, you got it? Okay, good job. Now, talking about average speed, in defining average speed, we can define it as the distance traveled divided by the time interval for the motion. That's how we define average speed. So when we get the average speed, yeah, basically you have to get the distance traveled, then divided it by the time interval for the motion. So take notice of the word distance, because later on you will see the difference between distance and displacement. Those two terms are different in physics. They are not the same. Now, we're done with speed. Let's have velocity. So velocity answered the question how fast and in which direction. Now, notice there is now involvement of direction. Okay, so of course, velocity is a scalar quantity, or rather, vector quantity. Vector quantity means it has both magnitude and direction. Again, it has both magnitude and direction. So a good example is 100 meter per second. We have the magnitude 100 meters per second, and then the direction is south. So this is a good example of velocity. Velocity, again, is a vector quantity, and it answers the questions how fast and in which direction the object is moving. Okay, so this you see the difference between velocity and speed? Okay, good job. Now, Average velocity. Okay, let's define it. Define as the displacement divided by the time interval during which the displacement occurred. You see the difference now. Earlier, if you observe, we defined average speed as distance traveled. You see the word distance, but in velocity, it is the term now is displacement, defined as the displacement divided by the time interval during which the displacement occurred. You see the difference, because average velocity is a vector quantity. That is why it used also the word displacement instead of using the word distance. Okay, so if you don't really understand what's the difference between displacement and distance, you need to have a review on displacement and distance. So this is just a review, so we're not going to focus that. But remember, displacement is a vector quantity and distance is a scalar quantity. When we talk about velocity, average velocity, we are going to use the word displacement, then divided by the time interval during which the displacement occurred. And when we talk about average velocity, we are going to use the word distance. See this? Distance. This distance. Okay. All right. Now, to check if you understand the concept of scalar and vector quantity, identify the following concepts: scalar, or rather, sorry for that. Check scalar or vector quantity. This will be your extra challenge. Okay, you can research on this. Right. So these are the terms that you can study to further understand the concept between scalar and vector quantity. You have example: speed, displacement, mass, temperature, force, and acceleration. That will be your task. That will be your challenge. Okay, research and try to figure out which among these quantities or concept is scalar and which is vector. Okay, so let's move forward. Now, let's talk about acceleration, which is our topic, because our topic for today we will be talking about acceleration, force, and free body diagram. Acceleration. Let's define acceleration. Acceleration is the quantity that describes the rate of change of velocity in a given time interval. So we have average velocity, average acceleration. Let's try to differentiate. In mathematical terms, you have average velocity that is equal to delta x divided by delta time. That is equal to final, x stands for displacement, okay, minus initial displacement over tf minus ti. Okay, tf means final time, and then ti stands for initial time. So in words, we can say that average velocity is equal to change in position over change in time. Okay, so x actually means position also. That is equal to displacement over time interval. So this is the mathematical equation. Okay, so don't worry, we don't have to solve problem regarding on this. At least we're familiar with the mathematical equation of average velocity. Now look at the difference between average acceleration. Okay, let's try to differentiate average velocity, average acceleration. So average acceleration, that is delta v over delta t. So talk about delta v, that is change in velocity. So bf stands for final velocity minus initial velocity over final time minus initial time. So in words, we can say that average acceleration is equal to change in velocity divided by time required for the change. That is the difference between average velocity and average acceleration. Okay, look at the difference here. Average velocity, you are going to use the displacement, then divided by time interval. Here, average acceleration, you are going to get the change in velocity. In getting the change in velocity, all you have to do is final velocity minus initial velocity, then divided by time required for the change. How do we get the time required for the change? Very simple. All you have to do is you have to final time minus initial time. So that is the mathematical expression about average velocity and average acceleration. Okay, right then. Now, let's have symbols. Speeding up or slowing down. So velocity and acceleration, we have initial velocity we have acceleration, we have motion. We have three columns. Okay, you see our table here. So we have, first example, we have, this is, again, we have three columns. We have initial velocity here, column. We have acceleration. We have motion. Okay. When the initial velocity is positive, that means plus sign, and the acceleration is positive, what does it mean? So meaning the motion is speeding up. Again, when both are positive, that means they are going to the same direction. That means the motion is speeding up. That is symbols in physics. Okay. Another, we have negative velocity and then negative acceleration. Still, the motion is speeding up. Why? Why is that speeding up, sir? Remember, they are in the same direction. This is negative, this is negative, so they are in the same direction. That means the motion is speeding up. Just remember. Now, let's have initial velocity is positive, but the acceleration is negative. What can we say about the motion of the object? The object is slowing down. Why is that, sir? If you observe this, the velocity is positive, the acceleration is negative, that means they are going to a different direction. This symbolizes, this positive velocity and negative acceleration symbolizes that the motion is slowing down. Again, this symbolizes that the motion is slowing down. Now, what if the initial velocity is negative and the acceleration is positive? So remember, they are not in the same direction. This is negative direction. This is positive direction. Of course, what does it mean? This motion is slowing down. What if the initial velocity is negative or positive, but the acceleration is zero? What does it mean to the motion? What does the motion mean? Means the motion is constant in velocity. We have constant velocity as long as it does not, that means it does not accelerate, because the acceleration is zero, therefore the velocity is constant. What if the initial velocity is zero and the acceleration is negative or positive? It means speeding up from rest. Okay, that means the object is stationary at first and then it moves, speeding up from rest. Again, when the initial velocity is zero but the acceleration is negative or positive, that means the object is speeding up from rest. Good job. Now, what if both the initial velocity and the acceleration is zero? That means, it simply means the object is remaining at rest, or the motion is remaining at rest. Okay? So these are the symbols. Okay. I hope you got it. Okay. Anyway, that's, if you don't understand what I mean, you can just review my video. That's the advantage of recording. This is the advantage of, having a class using videos and softwares instead of the actual classes. Because if you don't understand, you can just review. Okay. Now let's move forward. Now let's have some more examples so that you can really understand. Let's have this picture. You see a car moving. Okay. Car A is moving. It's the velocity is going to positive. That means going to the right. Okay. The acceleration also is going to the right. Okay, positive direction. So we have acceleration vector and velocity vector are in the same sign direction. That means it is a positive direction. Positive acceleration, rather. It is a positive acceleration. So that means car speeding up to the right. Again, acceleration vector and velocity vector are in the same sign direction. That is equal to a positive acceleration. They are both in the same sign direction. That means that is equal to car speeding up to the right or east. Speeding up to the right or east. Okay, let's have an example. B example. Okay, let's have this car. Acceleration vector is going to the right. And the velocity vector, or rather, acceleration vector is going to the left, rather, I'm sorry. And then velocity vector is going to the right. So the acceleration vector and velocity vector are in the opposite sign direction. That is equal to negative acceleration, which means car is slowing down as it moves toward the right or east. Okay. Again, velocity vector is going to the right. You have acceleration vector is going to the left, that is equal to a negative sign direction, negative acceleration, okay, because they're moving to the opposite sign direction. That means car is slowing down and as it moves toward the right or east, okay. So this is a good clear example of the previous signs that we discussed on the table. I hope you got it. Again, remember, if the in the picture A, the acceleration vector and velocity vector are in the same sign direction, positive, that is equal to positive acceleration, that is equal to car speeding up to the where? To the right or east. So acceleration vector, there's one going to the left, and velocity vector is going to the right, are in opposite sign direction. That is equal to negative acceleration, which means car is slowing down as it moves towards the right or east. Okay. All right, good. Now let's have car C. Okay, we have velocity vector is going to the left, acceleration vector is going to the right. So acceleration vector and velocity vector are in the opposite direction, or they're opposite. Velocity vector going to the left, uh, acceleration vector going to the right. So are in opposite sign direction, that is equal to positive acceleration. Positive acceleration. Okay. Car is slowing down as it moves towards the left or west. Very good. Positive acceleration, car is slowing down, it slows down because they are in the opposite direction. It's going to the left, negative, going to the right. Okay. That is positive. So that means the car is slowing down as it moves toward the left or west. Okay. Now let's have car D. Okay. Acceleration vector going to the left. Velocity vector going to the left are in the same side direction. Remember, same side direction because both of them are going to the left or going to the east, west rather. So that is equal to negative acceleration equal to car speeding up to the left or west. Okay, acceleration vector going to the left. Okay, and then velocity vector going to the left. Both are in the same side direction. That means negative acceleration, car speeding up to the left or west. Okay, let's move forward now. Let's talk about force. Okay, what have you observed with the picture? You see what do you see? You see family. You have the father, the mother, uh, kids are pushing the car. So what does it show? It shows force. Perfect. Okay. So our common sense idea of force is that it is a push or a pull. In this situation, in the picture, you see a push. So this is a good example of a force. Okay. Notice our careful choice of the words. We refer to a force rather than simply force. We want to think of a force as a very specific action so that we can talk about a single force or perhaps about two or three individual forces that we can clearly distinguish. Hence, the concrete idea of a force, quote unquote, acting on an object. So basically, our common sense idea is a force is a push or a pull. In the picture is a good example of a push. They're pushing the car. Okay, this is a picture showing a force, which is in this time it's a push because a force can be a push or a pull. You understand? Okay, got it. Good job. Now, don't do this. What do you see in the picture? Don't do this to your classmate. Okay? Okay, class? So let's describe more about force, describing a force. Okay. Remember, implicit in our concept of force is that a force act on an object. Remember, a force act on an object. In other words, pushes and pulls are applied to something. That something is an object. Okay. From the object's perspective, it has a force exerted on it. Forces do not exist in isolation from the object that experiences them. Okay, do you understand this? Okay, let's have an example of the picture. You observe the fist hit the face of a man, but don't do this to your classmates. Okay, this is just an example for a very good example of concept of force. Okay, remember this time The agent of the force is the fist, okay? And it hits the object, which is the face of the man, okay? So forces do not exist in isolation from the object that experiences them. That means the force from the fist does not exist only. It hits the face of the man. That means they are interconnected, okay? So from the object's perspective, which is the face of the man, it has a force exerted on it, okay? From the object's perspective, in this example, the face of the man, it has a force exerted on it by the fist. So again, implicit in our concept of a force is that a force acts on an object. We do that when you talk about the force, we do not do it uh, as in isolate, alone. We mean that we talk about force, it is acting on an object. Okay? Okay. You understand? All right. So let's describe force again. Okay. Every force, remember this. Remember this. Every force has an agent. An agent. Okay. Remember, every force has an agent. A force has a specific, identifiable cause. It should be specific and it should be identifiable cause. That is the agent. Agent. Okay. If a force is being exerted on an object, you must be able to identify specific cause. When we say specific cause, we're referring to the agent of that force. Let's have an example. The picture. What do you see in the picture? Good, right. You see a boy playing a takyan. Are you fond of playing takyan? I'm sure you are fond of playing takyan. Me too, and I was like you. All right. Now, let's study the boy. The boy there is playing takyan. Who do you think is the agent of the force in this situation? Good, you're right. It's the boy, or in specific, it's the elbow of the boy. So every time the boy do this, push or apply force on the takyan goes up. So what is the agent of the force that makes the takyan goes up? It is the boy. The boy is our agent. It is specific and identifiable, which means every force has an agent, which means force cannot exist by itself without an agent. In our example, the boy is the agent. That means the takyan cannot just flow up without the boy, right? So the boy, which is the cause of the takyan going up, is considered as the agent. It is specific and identifiable. Again, what is the agent of the force of the takyan going up? It is the boy, particularly the elbow of the boy. Good. You got it very perfectly. Okay. I like you, class. You're very smart. Now, again, let's talk about the force. Force is a vector quantity. Again, force is a vector quantity. Remember what we mean by vector quantity? It has both magnitude and direction. If you push an object, you can push either gently or very hard, correct? Similarly, you can push either left or right. That means direction, up or down. To quantify a push, we need to specify both a magnitude and a direction. You have to specify magnitude and direction because force is a vector quantity. It should have a magnitude, it should have a direction. Are you fond of playing billiard? Oh, good. I know you're fond of playing billiard. So there, in that example of the billiard, you can push, can hit the white ball. In Bisaya, we call it the bulamano. It's either strongly or gently, depends on you, and you can push it in the left, to the right, in what direction that you want. So in this case, force is a vector quantity. Okay? So let's summarize the concept that we have just learned. So we talk about force. Force acts on an object. Okay. Second, for every force has an agent. Okay, that means a force cannot exist by itself. It should have an agent. Okay? If you want to move the takyan up, there should be an agent. The takyan cannot just move up by itself. The agent in this case, in the example, is the boy. Third concept, force is a vector quantity. Again, what are the concepts that we learn about the force? Force, first we have as an agent, and then third, force is a vector quantity. Okay, got it. Now remember, force can be either be contact or non-contact. Okay, what do you see in the picture? We have there a man hitting the ball. This is baseball, right? Are you fond of playing baseball? I don't know how to play this one. On the other side, you have there a coconut fruit falling. So in this case, where do you think is contact, and where do you think is non-contact forces? Okay, for us to understand which one is contact and which one is non-contact force, let's watch this video. Are you ready? Okay, there we go. Okay. All right. So let's review. I hope you understand the video. So what is the definition of contact force rather on the video? The video defines force as still, push or pull. What is the definition of contact force in the video? Okay, anybody? All right, good. Now on the video, contact force is defined as the forces that exist on the touching object. Okay, it should be, the keyword is touching object. So that force exists on the touching object. Okay. What are examples of contact forces? Okay. Let's give some examples given in the video. So we have normal contact force. Okay. Right. Tension. Okay. These are examples of contact forces given on the video. Let's have normal contact force. So a good example is a box put on the top of the table. The box weight push, okay, the door in a downward direction, okay. And then of course the table also push on the opposite direction, upward. Okay, so the normal force is perpendicular, again perpendicular to the surface in contact. If you observe, this is a good example of a contact force because the box and the table are touching each other. They are physically contacting each other. Okay? So normal force is a good example of the contact force. The box, the table, physically touching each other. Okay? The box, because of its weight, the direction of the force is going down. And then the table also push the box going up with the opposite direction but in the same magnitude. If you observe the arrows, they are same in height. That means the magnitude of forces are the same, but the direction is different, opposite direction. The box push the table going down with this magnitude represented by the length of the arrow, and then the table push the box upward represented by this arrow in the opposite direction but with the same magnitude. This is an example of a normal force and a good example of the contact force. Second example of the contact force is tension. You observe this. The agent for tension force, remember class, the agent is the rope. You observe two boys, okay, having a tug of war. Okay, they pull the rope in opposite direction. So the agent of the tension force is the rope. You observe, this is still a good example of contact force because the buoys are touching or physically contacting the rope. Okay, so both normal force, normal contact force, and tensions are examples of contact forces because you observe there is a physical contact. Easy as that. Now, let's talk about the definition of non-contact force given in the video. So what is the definition of the non-contact force or forces given on the video? So let's define. So forces that exist on the objects that don't require to be touching. Remember the keyword, don't require to be touching. So what are examples? So we have gravitational force and magnetic force. We have gravitational force. For gravitational force, a good example is the Earth's gravitational force. Okay, this is an example of non-contact force because it has an influence on object even if we are not physically touching the Earth. For example, you're hanging on the rope. You can feel, or you're on the top of the building, and you want to jump, but don't do it. You want to jump. Basically, you will fall down. Why is that so? Because of the gravitational force. Even if you're not touching the Earth, but if you jump, definitely the gravitational force will act on you. It will pull you down. Just like when you jump on an airplane, the airplane is not touching the Earth physically, right? But then, of course, when you jump from the airplane, you will fall down because the gravitational force will act on you. It has an influence on you. So even if you're not touching the Earth, but still you will fall down. So therefore, gravitational force is a good example of a non-contact force. Aside from gravitational force, you have magnetic force. Okay, you've tried this one. Okay, so in the picture, if you observe, even if these metals clips will be far away from this is the magnet, the metals, the clips will move and then attracted to the and then attracted to the magnet. So see, there is no physical contact at first, but even if the clips are far away at first from the magnet, it will move and be attracted to the magnet. So therefore, magnetic force is a good example of a non-contact force. Okay, you understand? Ah, aside from magnetic and gravitational force, another example of non-contact force is electrostatic force. Okay, this is a good example. Okay, this is a woman in the picture. A woman, an example of static electricity. A girl's hair stands on end as she touches a Van de Graaff generator. If you observe, okay, the hand she's touching the Van de Graaff generator, but look at the hair. It's very far from the generator, but it moves. It moves up. It stands on end. Okay, so this is a good example of electrostatic force. You cannot see the hair is physically uh, touching or contacting the Van de Graaff generator, but still the hairs and goes stands up. Okay, so this is an example of non-contact force. Again, so what are the example of non-contact force? We have gravitational force, magnetic force, and electrostatic force. Okay. Now, so assessment. Let's try to check your understanding on forces as contact and non-contact force. So you are going to identify if the force acting on the given situation is contact or non-contact force. Are you ready? Let's. You will be given pictures and situation, then you are going to answer if contact or non-contact force. You can write this in your 1/4. All right, first picture. Ready? It's first picture. An apple falling down from a tree is one of the best examples of what force? Okay, got it. Very good. It should be non-contact force. So what kind of it is non-contact force? Because what force, specific force is acting on the apple? Why does it fall down? Because of gravity. And gravity is a good example of non-contact force. Good job. Now number 2, let's have a box sliding down a slope. Remember, we're focusing on friction, not on gravity. What is that? Okay, good job. You have contact force because the box is touching the slope or the ground. In that case, it is the contact force. Now, let's have the charging of the hair and attraction of paper bits towards it. If you observe, when you try to comb your hair, and then after combing, you are going to get close the comb to a piece of paper clips or paper bits. You see the paper bits are attracted towards the comb. So in this case, what kind of force is this? Of course, it is non-contact force. Why is that so? Because it's an example of electrostatic force. Electrostatic force. Now, next, we have iron pins attracted in the presence of a magnet bar without any physical contact. At first, the iron pins are far from the magnet, but later on it is attracted. Why is that so? What kind of force is this? It should be non-contact force. This is an example of magnetic force. Therefore, magnetic force is non-contact force. Good job. Now, last, we have number 5, a man pushing the box. We're focusing on applied force. Okay. Applied force, force applied to an object by a person or another object. That's the meaning of applied force. What do you think? Is this, what type of force is this? Non-contact or contact? Good job. This should be contact force. Applied force is an example of a contact force. Now, okay, let's talk about agent of forces. Let's have pictures. We've been talking about force. Every force is an agent. Okay, let's have the rope. In this first picture, you have box, okay, represented by a dot, and then pulling force of rope represented by the arrow. Actually, we are moving forward to our third concept, free body diagramming. But we'll start first with this picture so that you will be able to understand. Let's have the box. Let's have a man pulling the rope. Okay, the box is represented by the circle, and then pulling force of a rope represented by the arrow. Okay, with the direction going to the right. So in this case, what is the agent of the force? The rope is the agent of the force. So that is why this kind of force is called tension force, because of the presence of the rope. Let's have the second example. You have box the spring, okay, box again, represented by the dot, and then the pushing force of the spring represented by the arrow. Okay, the spring is the agent of this force. The direction is going to the right because the spring will push to the right, in the direction of the right. The spring will push the box in the right direction. So in this case, in this second example, you have the spring as the agent. Still, this is a good example of the tension force, a spring force rather. This is a good example of a spring force. So the agent is the spring. First example, the agent is the rope. Second example, the agent is the spring. Okay. Third example is a box, and then represented by the dot, and then long range force of gravity. This is the ground. Okay, the ground. So you have, in this case, what is the agent of the force? Of course, the earth is the agent of the force. Okay, review. Let's review. First situation, what is the agent of the force? You have there a man or a girl. This is someone pulling a box using a rope. So the rope is the agent. You have there the spring on the box. So the agent is the spring. This third example, what is the agent of the force? You have the gravity, or the earth rather. Long range force of gravity. The agent of the gravitational force is the earth. Okay, the gravitational force pulls the box down. Okay, you have the direction. It's going down. FG, you have there the arrow. That means a vector quantity. That's a direction. G stands for gravity. F stands for force. That's the direction. It's going down. So the pull of a planet on an object on or near the surface is called what? The gravitational force. The agent for the gravitational force is the entire planet, not a specific part of the planet. Remember, it should be the entire planet. The gravity acts on objects whether moving or at rest. Now, let's have the spring. Okay, you have a compressed spring exert a pushing force on an object. When you compress the spring, it will cause is pushing force. You observe going to the right. When you compress the spring, this box, you will push that going to the left. The spring will push also in the opposite direction going to the right. In this example, letter B, a stretch spring exert a pulling force on an object. It's a reverse. If we are going to stretch, in this side, you're going to inat the spring. What is the direction of the force? It should be going to the left. As stretch spring exert a pulling force on an object, it will pull. In this side, birahon niya ang box. Kari siya sa first example, imong gi-compress, giipit ang spring o sa button sa spring. What will the spring do? It will push. It will exert as pushing force. Push you going to the right. Push the box going to the right. In this case, when going to stretch inaton ang spring, what will happen? What is the direction of the force? It will, the stretch spring exert a pulling, birahon, pulling force on an object. The direction is going to the left. Okay, spring exert one of the most common contact forces. A spring can either push when compressed. Remember, when you compress a spring, what is the force exerted? It will push, or a pull when it is stretched. Now, when a string or rope, this is tension force, a rope exerts a tension force on the sled. When a string or rope or wire pulls on an object, it exerts a contact force that we call the tension force. Because of the presence of the rope, the agent is the rope, so we call that tension force. The tension within a rope and the tension force experienced by an object at the end, in this case, the sled, of the rope are really the net. That are really the net spring force being exerted by billions and billions of molecules. Okay, this is a different explanation because the rope is made about billions and billions of atoms, of molecular bodies or atoms. Okay. Right. Now let's have this normal force. So the force exerted by a surface, the surface here, the agent is the surface, against an object that is pressing against the surface is called as the normal force. In this example, you have there the physics books put on the top of the table. In essence, the normal force is just a spring force, just like a spring force, but one exerted by a vast number of microscopic springs acting at once. So, you see the difference now between normal force and spring force? There, the agent is spring. But in this case, for normal force, it could be a surface. Okay, surface. In this case, physics books on the top of the table. The agent of the normal force is the surface of the top of the table. In this case, a girl pushing the wall. The agent is the of the normal force is the surface of the wall. Okay, the compressed molecular springs in the wall pressed outward against her hand, meaning the direction of the force applied force by the girl going to the right, and of course the wall also will push in the same magnitude but in opposite direction going to the left. In this case, physics books on top of the table, normal force, the agent is the surface of the table. The weight of the books push the surface of the table downward, but the normal force of the table will push in a different opposite direction but at the same magnitude going up or upward. Okay, so hopefully you understand. Now let's have friction. Okay, we're done with normal force, spring force, tension force. Let's talk about friction. These are contact forces. Friction is an example of contact force again. Friction, like the normal force, is exerted by a surface. See, still the agent is still the surface, just like the normal force. But what's the difference? But whereas the normal force is perpendicular, remember, normal force is perpendicular to the surface. The friction force is always tangent to the surface, not perpendicular. That's the difference between surface, normal force, and frictional force. Normal force is perpendicular to the surface. Frictional force is tangential to the surface. Let's have an example. You have there uh, this one. Okay. Let's have the diagram. You have there kinetic friction opposes the motion. You have there a boy riding. This is a sled. Okay. So the velocity is going to the right. Okay. That's the movement. But the kinetic friction, what is the direction? It should be in the opposite direction. Okay. So in our diagram, you have there the object of interest, which is the boy riding a sled. Then the direction of the fraction key. F key stands for kinetic fraction because why is it kinetic, sir? Because it's the sled is moving. This one is moving. It's kinetic. So if you observe, the kinetic fraction is going to the left, and then the velocity is going to the right. They are in opposite direction. So always a fraction is always opposite to the direction of the velocity or the motion. Observe this. Now let's have, there are two types of kinetic fraction. It could be there are two types of fraction rather. It could be kinetic fraction or static fraction. So this is a good example of kinetic fraction because this boy riding on a sled is moving, so motion related to kinetic. Okay, that's simple as that. Okay, that's why it's called kinetic because there is motion. Here, another type of fraction is static. Static. Okay. Static friction acts in a direction that prevents slipping. We have there the frog on a slope, but the frog is not slipping down. What she almost slides are both in Visaya. So where is the direction? What is the where is the direction of the static friction? The static friction acts in the direction that prevents slipping. So what is the direction that prevents slipping? It should be going up. Going up. So again, our dot here represents the frog, and then the arrow represents the static fraction. Why is it static, sir? Because the frog is actually not moving. Okay. So what is the direction? It should be in the direction that prevents from slipping. So what direction prevents slipping? It should be going up. Going up. So basically, main idea. There are two types of fraction: okay, static fraction and kinetic fraction. Fractions are both static fraction and kinetic fractions are both contact forces. Okay. The difference between friction and normal force is the normal force is perpendicular to the surface. On the other hand, friction is tangential. Tangential. But they have the same agent, the surface of the object. Similarity between friction and normal force is the agent. Both the surface of the object is the agent, but the difference between them is that normal force is perpendicular. Direction of the force is perpendicular to the surface. For friction, the direction of the force is tangential to the surface. Okay. So with my examples, I know you are now exposed to, you have this the dot and the arrow. These are examples of free body diagramming. Later on, we will have more. We'll have deeper explanation and the discussion on free body diagram because I will ask you to do the free body diagramming. Okay. Right. Let's have free body diagramming. In short, FBD. Okay. What does FBD stands for? That's free body diagram. Okay, there are tactics in drawing force vectors. So these are rules or guidelines in making a free body diagram. So first, represent the object as a particle. In this case, this one particle. Then second, place the tail of the force vector on the particle. This is the tail. You have to place that tail of the arrow. Is the tail. Okay. Then draw the force vector as an arrow. Yeah, there you go. Okay, pointing in the proper direction and with the length proportional to the size of the force. It should be with the length. It should be pointing in the proper direction, where the direction of the force is going, and with the length proportional to the size of the force, which means the longer the arrow, that means the greater is the force represented. Okay. Fourth, give the vector an appropriate label. That means you are going to give the vector force or the force an appropriate level. Could be tension force, should be fractional force, it would be normal force, gravitational force. Those are the labels of the force. Okay, again, first, represent the object as a particle, our object of interest, particle. Second, place the tail of the force vector on the particle, this one. This is the tail of the arrow. Then draw the force vector as an arrow. This is the force vector. Okay. And then in the proper direction, whether going up, going down, going to the left, going to the right, okay, depending on the type of force that you are trying to imply. And with the length proportional to the size of the force length. Okay, the longer the length of the arrow, that means the greater is the force. Simple as that. Let's try an example. Let's have free body diagram. Situation: a skier is being towed up a snow-covered hill by a tow rope. So you have here a skier. I hope you're familiar with skier. Usually, people from the America, Europe, they do skiing, especially during winter. But we don't have like here in the Philippines, I guess. So a skier is being towed up a snow-covered hill by a tow rope. There, the rope, tow rope is being pulled up, going up. This is the skier. What forces are being exerted on the? Let's have this. Let's try to edit. It's not. It's very big. There you go. Okay. So what forces are being exerted on the skier? Okay. You remember the technique in doing vector forces? First, we have to represent the object as a particle. So we have to identify the object of interest. In our case, what is our object of interest? We focus here. Here, the object is the skier. This is our object of interest. We draw a circle. Oh, okay. This is our object of interest, the skier. Second, draw a picture of the situation. So here is this is the situation, and this is the drawing. Third, draw a closed curve around the object. Closed curve, this one. Sorry, this is the circle rather. Course, this is closed curve. Fourth step, locate the points where other objects touch the object of interest. Locate the points where other objects touch the object of interest. Okay, let's have this one. This is the rope and the hand of the skier. So this is, we locate one object touching the object of interest. Our object of interest, remember, the skier, this man. So this is, there is a point where the object touches the object of interest. In this case, the rope is touching the rope. Okay. Then here the rope on the ground touch the scare. Also, aside from the rope, there's also the ground touching the scare. Name and label its contact force. The rope exert a tension force. In this case, remember, when there is a presence of rope, rope as an agent, automatically the force is called tension force. Okay, and the ground exert rather both normal, okay, normal force, okay, and of course a kinetic friction. Okay, and of course we also have there the gravity. The name and label long range forces. Gravity is the only one. So long range forces, okay, of course, the reason why the scare having difficulty moving up is because of gravity. So of course we assume gravity is always involved there. Now, next, let's have the diagram now. Okay, again, identify the object of interest. This is the object of interest. And we are going, based on our discussion, we are going to represent the object as a particle. Our object of interest is a sphere, so we represent it as a particle. Draw with that, a particle, this one. Okay. Next, this particle represents the object of interest, which is the sphere. Uh, Next, place the tail of the force vector on the particle. Okay, let's place the tail. For the tension force, what do you think is the direction of the tension force? Okay, the tension force should be going up because the rope will pull the scare up. So there, tension force going up. Okay. For the tension force, what is the opposite of the tension force? Okay, why is that so? That the scare is having difficulty going up. One of the reason, the opposite for the tension force is the kinetic friction. Okay, kinetic friction. Okay. Now, sir, when we draw the tension force, the length, its direction is going up, but the length is quite long. This represents that the force vector applied on this tension force is greater compared to the kinetic friction. Why is that, sir? Because obviously the tension force should be greater in magnitude compared to the frictional kinetic friction force, because that's the purpose of the scare. He has to move up, so the tension force should be greater. If it is the same in length, so the scare will not be moving up. It will be staying here. Okay. Again, you have the tension force going up exerted by the um, rope, and the magnitude should be longer compared to the kinetic friction. Next, aside from this tension and kinetic friction, another force is normal force. Remember, this is a surface, and the surface will always exert a force on the feet of the skier. So that force exerted by the surface is called a normal force. And look at the direction. It is perpendicular to this is the surface. It should be perpendicular. Remember, for normal force, it should be perpendicular, 90 degree. And then opposite to the normal force is the gravitational force. That's what makes the skier touching on the ground because of gravity. Okay. And remember, why not, sir? It should be, why not opposite, sir? Why is it different, sir? Remember, the gravitational force should be going to the center of the Earth. So the only direction that goes to the center of the Earth is like this. But look at the magnitude of the normal force and the gravitational force. They are the same in length. That means the normal force exerted on the scare is the same, because or else the scare will be floating if not the same. Should be equal. That's why the scare stays on the ground, because the normal force and the gravity, they're equal in the magnitude. That's why the scare stays on the ground, or else it will be floating. But on the other hand, the tension and kinetic friction, they are the opposite direction and not the same in magnitude. The tension force is greater because remember our concept, the scare should be moving up. Okay? If it is equal, then the scare will not be move up. The opposite to the tension force, what makes it difficult to pull the scare, it's the friction of the ground. Go opposite. Okay. There you go. So that's how we make a free body diagram. Okay, again, first step, identify the object of interest. In this case, the scare. Draw a picture of the situation. This is our situation, and we have drawn a picture. Draw a closed curve around the object. Okay, these are object of interest. Then next, locate to the points where the object touch the object of interest. So you observe there the rope touch the object of interest, the sphere. Also, the ground touch the sphere. So this is the point where other object touch the object of interest, the sphere. Name and label its contact force. We are able to name. For this one, normal force, you have kinetic force, gravitational force, and tension force. So and then name and label long range forces. Gravity is the only one. So long range forces like the gravity. Gravity is always present in this case. As long as you are on Earth, you're active by gravity. Okay, so this is our free body diagram. This is the situation. This is the drawing, and this is our free body diagram. Okay, I hope you can make your own. Let's have assessments. So this is group or individual activity. Okay, you can do it by group. But if you are at school, so you can do it by group, or if you are studying online at home, you can do this individual. So each group or each individual will provide a specific situation to which they will construct a free body diagram to model the forces acting on the object of interest. After 10 minutes, for the group activity, post your groups in your designated area. Select a member from the group to explain the diagram in a parallel walk. Each group will be given 2 to 3 minutes to review and comment on the outputs of the other group. This is for the group activity if you are at school, and you can apply also this individually if you are studying online. Okay. This is the processing questions. What commonalities can be seen among the outputs of the other groups? What can you say about the quality of the outputs produced by the other groups? Can you suggest ways to improve how free body diagrams should be drawn? So assignment. So assignment, you are going to research on what is the first law of motion. Okay. So thank you very much. So thank you. See you in the next topic. Our next topic will be balance and unbalanced forces and the Newton's first law of motion. Okay. Again, I told you that this is a foundation for the second law of motion. You have 3 laws of motion for Newton, and what we are trying to study now is the foundation. Thank you very much. You have a good day.